Hi guys, today we're going to start our very first lesson in Algebra 2. And to get started, this whole unit is going to be a real foundational building block. A lot of it's going to be stuff that you've seen before, and it's just going to be something that we kind of use to refresh our brains, kind of start thinking in math terms again, but also something that we're going to use to build on throughout this year. So without further ado, we're going to start today with some properties of numbers. So numbers are this kind of like 1, 2, 3, but there's also things like 1.5 and 7 halves and the square root of 27, things like that. So we need to start taking those numbers and dividing them into groups. There are some real numbers that belong to more than one group, and there are 5 groups. Now, some of you might be going, real numbers? Are there fake numbers? No, but there are imaginary numbers, and we will talk about those later in the year. Something to look forward to. It's really fun, actually, I promise. Natural numbers are the ones that you count with. So that would be like 1, 2, 3, 4. When I ask you to count to 10, that's how you would count. Whole numbers are just the natural numbers plus 0. So literally the only difference between natural and whole is that there's 0 involved. The dot, 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 I'm using that to show that it goes on and that there's more numbers that fit this criteria. Next we have, there we go. Naturals, they're numbers and zeros. So naturals, going back to the base that we've got there, 1, 2, 3, 4, 0, all right, but then it's also got the opposites of the naturals. So this would be numbers like -1, -2, etc. So basically anything that is just like, if we put a decimal, the only thing following it would be a 0. We never write that decimal, but it's there. It's just kind of acknowledged that this is 4.0. So then we get into the more complicated ones, and these give people a little bit more difficult of a time figuring out which one's which. The first one is rational numbers. So rational numbers are all numbers that can be written as a fraction. So 1/2, 2/3, 7/8, anything that can be written as a fraction, plus anything that is an integer and terminating or repeating decimal. So terminating means it ends. So things like 0.12, it just stops there. Repeating decimals would be like 0.12222, and if it just kept going on and on forever. It includes fractions and square roots that simplify to any one of those things. So a square root that simplifies to an integer, terminating or repeating decimal, fraction, would be a perfect square. So a perfect square could be 25. If I take the square root of 25, I get 5. These would all be examples of rational numbers. And then finally, there's irrational numbers. And irrational numbers are anything that cannot be fractions. So something like 1.2 over 3.6 is not a fraction because we don't do decimals within fractions. By definition, that's not a fraction. Decimals that never end or repeat. So let's see. If I have 0.1793246, I'm just making this up off my head, so I'm not repeating anything. If I were to say that kept going on and on, then that would be no pattern is seen there. I don't see any repeating numbers, and it doesn't end, so that would be irrational. Square roots, a classic definition is the square root of 2. The square root of 2 is approximately 1.41, and it goes on forever. But it, again, doesn't repeat. Basically, the main things that you're looking for with irrationals are non-repeating or ending decimals and square roots. Do you think that there are any fractions that could fit this definition? Like if I take 1/2, I can convert that to a decimal of 0.5. Now that one's an obvious, like it ends. Can you think of a fraction that does not end or repeat? Actually, there are none. There are no fractions that fit this criteria. And so there are no fractions that are irrational numbers. If you're intrigued by that and you want to know more, let me know. Maybe we could set something up, have a conversation about it. I don't know. We'll see what would come of that. So what does this look like? I don't do well with remembering these things just off the top of my head, so I needed a little bit of a visual. So remember, the first thing that we started with were the natural numbers. So it's like the natural numbers, or those numbers that we count with, just kind of got together and started their own club. And then 0 came along and said, guys, I want to be included. And so they added it. But notice that they kept themselves like a pretty tight group. So they kind of created a whole new club with themselves at the center of, not center, but like within it. And then the negatives were like, guys, we're sick of everyone like saying that we're negative, we're not fun to be around. And so they formed a club called the integers. Now again, the negatives can come and hang out in that club and in that space, but they can't get to this inner sanctum, if you will. That's not the right word. But like they can't get to the inner circle. There we go. That's what I'm trying to say, of the club. And then we've got the rational numbers. There we go. So kind of thinking of it as a hierarchy, you can also say that, well, we'll just leave it at that. If you want another illustration, I would be happy to share that with you. This is my favorite though, because it helps, I think, the most. And then irrational numbers are just kind of over here doing their own thing. They don't get to join the club. They're not a part of any of those. So if I had the number 5, and I said, what subsets does this belong to? Its most simplest one that it belongs to is natural. But natural is part of whole, so it's also a whole number. It's also an integer, and it's also rational. So in other words, whatever the number is, where I kind of put a dot where it is and then just draw a line all the way out and say, okay, it belongs to all of these. If I had the number -3, that is an integer. It's not natural because I don't count with it. It's not whole because it's not 0 or counting. So it's got to be an integer. And then that means by definition that it has to include also, or it has to also be rational. So let's look at putting these in order. We're going to classify them, put them on the number line, and we're going to see where we go from here. So I'm just going to put these in order from least to greatest. So the first one is 0. Then we've got -3.3 is going to be somewhere to the left of that since it's negative. -7/2. If I check that in a calculator to see what it is, oh, why did I put 2 negatives? Then I will find that it's -3.5. I will often change fractions and square roots to decimals in order to compare them. -3.5, and that would go over here to the left since negative gets bigger from right to left instead of left to right. If we do that, you're going to get 2 point something. I think it's like, I don't even know, it doesn't matter. 4 would go up here. So what I'm going to say is that this was -7/2, so I'm going to rewrite it in terms of like the original numbers. So -7/2 is, it's a rational because it's a fraction. -3.3, it's a decimal, so then I have to look at, does it terminate or end? It does, because it ends, so this would also be rational. 0, it is a whole number. The only reason we have another category called whole numbers. We've got square root of 5. Square root of 5 did not simplify to an integer, so therefore it is an irrational. Uh-oh, I'm going to run out of room. There we go. And then 4 is a good old natural number. And if I plot these on the number line, we're going to get something like -3.5, -3.3, and those are just going to be real close together, and that's all right. 0, square root of 5, which is 2 point something, and 4. Notice that right now, the reason I don't care what it is, 2 point what, is because when it comes to, I only needed to know the decimal so that I could put it in order. I just needed to know if it was bigger than 4 or less than 4. And so, and to plot it on the line. So once I know that it's 2 point something, there's not like specific marks of 2.1, 2.2. So I can just kind of estimate it, and that's all right. All right, some other important words that you've probably heard are the words opposite and reciprocal. Opposite just means switch the sign. Reciprocal means flip the fraction. With opposites, this would be something like -2 and 2. One way to check if two numbers are opposites is to add them together, and if you get 0, then they are opposites. One way to check if things are reciprocals is to multiply them. So if I have 2/3 and 3/2, and I multiply those together, I'd get 6/6, which is 1. And that checks out. So that's how I know that they are reciprocals. I can also just look and see that they are flipped. All right, using the same 5 numbers from the last example, find the opposite of each and the reciprocal of each. I'm going to start from the right because I don't want to work with 0 just yet. 4, the opposite is just going to be a negative, and then the reciprocal of 4 is going to be 1/4. Square root of 5, this one's a little tricky. The opposite would be negative square root of 5. It's important that that negative goes outside the radical and not inside. And then when I'm doing the reciprocal, for now, I'm going to say it's okay to write just 1 over radical 5, even though several math people just cried a little bit. That's okay. For now, it will be okay. -7/2, the opposite would be +7/2, and the reciprocal would be 2/7. Don't know why that took me a second, sorry. And my bad. -3.3 would, the opposite would be +3.3. When we're doing the reciprocal here, again, this really is not appropriate to write it like this, but for the sake of this, just to kind of get your head thinking that reciprocal means to flip the fraction, it's fine. 0 is the only case where I won't really let either of these slide. Technically, this looks like +0, so we could say, oh, that's -0, and then the reciprocal is 1/0. But remember, we can't actually divide by 0, and -0 doesn't matter. So really, it doesn't have an opposite or a reciprocal.